Hello everyone, I'm Norman Wildberger and welcome to the Algebraic Calculus. In today's very important video, we are going to establish the most fundamental formula in the Algebraic Calculus, which is this one right here. And what we're doing here is providing a new direction or a new way of thinking about integration. And the notation here, the setup, the point of view is quite different, but you'll see that it ultimately allows us to recover the same information as the classical way, except it does so without any limiting processes. So there's no limits involved, there's no rectangular subdivisions, trying to make lots of sums and then take limits of sums. We're not doing anything like that. It's a very different approach. Okay, but you'll see it's very powerful. In fact, the setup here is actually more general and I think more geometrically natural than the usual one. Okay, so let me explain what's happening. So we're in the usual two-dimensional plane and now we have a curve. And we're interested in areas determined by curves. Now, let's say we have a parabola like y equals x squared, okay? We're not actually primarily interested, at least at the beginning, in terms of areas underneath the curve. That's usually what one does. One takes a piece of the curve and looks at the area underneath it above the x-axis. Here, what we're more interested in is something in the spirit of Archimedes. It's a segment of the parabolic arc. In particular, what we're doing is we're looking at a segment of the curve from the origin and looking at the wedge-like area that's formed by going along the curve a certain piece and then coming straight back. So it's this area here that we're trying to, first of all, define and then compute. And I have to emphasize that it's the definition here that's really perhaps the most important thing. We're trying to get at what this concept should be. And we're doing it in a rather indirect, perhaps even a sort of tricky kind of way. So the fundamental formula is the one I gave you last time. It's this one here. And it's telling us what happens in a very important special case. When we have a curve given by a polynomial parametrization. In this case, alpha to the m, alpha to the n. So m and n are natural numbers. This is then a curve. And we're interested in the signed area of this thing from 0 to 1. That is when the parameter, you can think of it as alpha, the parameter runs from 0 to 1. So when we're at 0, we're at the point 0, 0, and at 1, we're at the point 1, 1. So all of these curves are going from 0, 0 to 1, 1. And we're getting curves that look like this or this or this. Okay, and the formula is that this thing turns out to be n minus m divided by 2 times n plus m. So the difference divided by the sum, and also a factor of 2. So for the y equals x squared situation, the curve is actually given parametrically by alpha and alpha squared. So it corresponds to, like, you know, x and x squared. There's the x coordinate, there's the y coordinate. This is a parametrization of the parabola. And we're going from 0 to 1, and the formula tells us that it's the 2 minus the 1 divided by 2 times the sum, which is 3. So altogether, 1/6. That's a number that we've found already via Archimedes. Another example, y equals x cubed. Okay, so this is now parameterized by alpha, alpha cubed. The same formula tells us that the signed area from 0 to 1 will be 3 minus 1 divided by 2 times the sum, which is 4. So altogether 2 over 8, or 1/4. Here's something quite different. The curve is alpha to the 5th alpha squared. So in terms of an equation, that would be x squared equals y to the 5th. Okay, maybe it looks something like this. And in this case, the signed area is going to be, well, it's going to be sort of having in this kind of direction. So we expect something to be negative as opposed to these ones where we got something positive. And the formula, what does it tell us? There it is there. S01, alpha to the 5th, alpha squared. It's 2 minus 5, the difference, divided by 2 times the sum, which is 7. So altogether, minus 3 over 14. Now in classical calculus, you would describe this curve in a different way. You would say, this is the curve y equals x to the 2 over 5, involving a fifth root of x, or x squared. Well, there's no way we're going to think about it that way, because that involves irrationalities and it involves infinite processes that are off the page. So that's definitely not the way we're going to think about things. This is the algebraic curve, and more importantly, this is the polynomial parametrizations of the curves. That's what we're really interested in. Okay, so we're after trying to establish the meaning and the actual value of this formula. So this is the fundamental formula of the algebraic calculus. So our strategy to prove this formula, and prove that it actually works, is sort of twofold. In this first part, what we're going to do is we're going to establish that if we have a notion of signed area that is natural in the sense that it satisfies the 5 properties that we've established for linear ones, then it has to be given by the formula that I've shown you. And then in the second part, we're going to then prove that that actually does work. Okay? So in this first part, I want to start by assuming that we have numbers, signed areas, S from T to U of PQ, for any polynumbers P and Q, and for any numbers T and U, such that these 5 properties always hold. Okay, and the properties are, first, the normalization property, that S0, 1, 1 alpha is a half, that S from 0 to 1 of alpha 1 is a minus a half. The additivity property, that the signed area from T to U of a curve plus the signed area from U to V of the curve is the signed area from T to V of that curve. And then here are the linearity properties that we've already seen a couple of times. The translation property, that tells us what happens when we shift by a constant, both endpoints by constant. We have to adjust by correspondingly shifting the polynomials in question. And the dilation property, property E, which is the same kind of thing, what happens when we dilate the factor, the endpoints T and U by a factor C, means we all have to compensate by augmenting the polynomials by changing them with factors in there. So we get P of C alpha, Q of C alpha. Okay, so that's our strategy. We're going to assume that we have some allocation of numbers like this satisfying these properties, and we're going to deduce just from these properties. Then there's actually no choice about it. There's no leeway. It has to only be one possibility, and that's the possibility that's described by that fundamental relation just for those pure powers. The signed areas of those curves formed from pure powers alpha to the m and alpha to the n. So this argument that I'm going to present to you is a variant of one that I published actually in 2002. Didn't realize it was that long ago. It was called A New Proof of Cavalieri's Quadrature Formula, and it appeared in the American Mathematical Monthly, volume 109, number 9, November 2002. Only 3 pages, 843 to 845. So that was the basic idea, but it was really in the traditional point of view where you're looking at areas under curves of traditional sort of polynomial functions. This is a more general situation. I think this is a somewhat more beautiful argument, although it's very much inspired by this paper. Okay, so it's important for those doing the course that you follow this argument very carefully, and I want you to understand all aspects of it. All right, so it's the core argument. It's a little bit subtle. We have to go carefully, and but it's actually not too hard. Okay, so the first thing that we're going to do is going to introduce some notation for the quantities that we want. We're interested in these numbers, S sub 0 to 1, alpha to the m, alpha to the n, and I might make that a definition, make it clear. So we're defining these numbers a sub mn, okay? And it's these quantities that we want to obtain a formula for. We'll call this equation 1. Okay, now let's observe that for any number c, if we're interested in the signed area from 0 to c of the same curve, alpha to the m, alpha to the n, then by the dilation property E, we can rewrite this as the signed area from 0 to 1 of c alpha to the m, c alpha to the n. So we're bringing the factor of c, which is currently here, taking it out of there, leaving just 0 to 1, and putting it inside the two components of the curve. Now, this is just c to the m, alpha to the m. This is just c to the n, alpha to the n. And now we have a situation where we have some constants here multiplying these polynumbers. So the linearity property, property c, allows us to pull them out front. We can pull a c to the m out front and a c to the n out front to get a total of c to the m plus n out front. And then we're left with s from 0 to 1, alpha to the m, alpha to the n. In other words, this quantity here is c to the m plus n times the quantity that we've defined to be a sub mn. That's explaining why this is actually sort of the fundamental quantity. If you know this one from 0 to 1, then you can calculate it from 0 to c relatively easily just by scaling it. And if you want it to say from b to c, then you just take the difference of two such things and you're going to get that one there. So it's really, this is really the sort of the core thing that we're interested in. And now we have this new, somewhat extended formula. We're going to call it Formula 2. So our aim is now to make some clever algebraic manipulations and try to extract something. And in fact, it's very much in the spirit of what Cavalieri did, back in the 17th century. So what we're going to do is we're going to look at this particular expression, the signed area from 1 to 1 plus c of alpha to the m, alpha to the n. What is c? C is just some number. Okay, it doesn't have to be bigger than 1. It can be any number because all of these things are algebraic. It doesn't matter where things are from. Okay, so what do we know about this thing? We know that this can be written by additivity, by the property B, as a linear combination here. It can be written as the signed area from 0 to 1 plus c of the same thing minus the signed area from 0 to 1 of the same thing. So we're using exactly the additivity property and just sort of rearranging it. Okay, now having this, we're going to use what we've just calculated because we know how to get a signed area from 0 to something. Okay, this first term is going to be 1 plus c, the thing that's up here, to the m plus n, because there's an m and n here, times a sub mn. That was the formula on the previous page that we called 2. And this one here is just a sub mn. That's the definition of a sub mn. So we have an expression for this particular quantity involving a sub mn and some polynomial in c. And we're going to call this formula 3. Okay, now we're going to look at the same quantity, however, from a different point of view. Because the same quantity can be re-expressed by using the translation property. See, we have a 1 here and a 1 plus c. So that's like 0c, but with 1 added. Okay, so we're going to use the translation property D to rewrite this as signed area from 0 to c of 1 plus alpha to the m instead of alpha to the m, and 1 plus alpha to the n instead of alpha to the n. Okay, great. And now these two things we can expand by using the binomial theorem. So the binomial theorem is the main algebraic tool that we're using. It's quite remarkable. The binomial theorem is so intertwined with the foundations of calculus. Okay, so what is the binomial theorem? How do we expand that? Well, I'm using summation notation here. I hope this is all familiar to you. We're taking 1 plus alpha to the m. So that's a polynomial in alpha. And the coefficients are binomial coefficients. M choose k. K is going from 0 to m. The powers of alpha are increasing from alpha to the 0 all the way up to alpha to the m. All right, so that's just the binomial expansion of that. And exactly a similar way, here's the binomial expansion of 1 plus alpha to the n. We're using a different index, j equals 0 to n, and choose j times alpha to the j. Okay, that's the binomial theorem. And now we're going to use linearity on this thing here. Okay? This is a polynomial in alpha. Here's another polynomial in alpha. So we can use the linear property of the signed area, which we can write very pleasantly like this. We can take the summation outside, summation k equals 0 to m. We can take this summation outside, summation j equals 0 to n. These binomial coefficients are like constants, so they come out m choose k and n choose j. And then when we've done that, the terms that are inside the summation are what's left over, the s from 0 to c of just alpha to the k, alpha to the j. So we're using the linearity here in a very strong way to take the sum out and just end up with a sum of individual powers. So a little bit like the example that I did in my last video. And we'll call this equation 4. So we now have two different expressions for the same quantity. This quantity and this quantity are the same. So we have equation number 3 for it, and now we have equation number 4 for the same thing. So let's put those two things together and just sort of clean them up a little bit. So the first one, the equation 3 that we had, the signed area from 1 to 1 plus c of alpha to the m, alpha to the n, we can now pull out the factor a sub mn, and we have 1 plus c to the m plus n minus 1. And the other one was the summation, so summation k equals 0 to m, summation j equals 0 to n, m choose k times n choose j. Then what was over here was signed area from 0 to c of the curve alpha to the k, alpha to the j. But by equation 2, we can rewrite that as c to the k plus j times a sub kj. Okay, so let me I want to make sure that we understand that. So here is what we just had. Right? We got to this point here, and I'm saying that this quantity here can actually be rewritten using property 2 as c to the k plus j times s from 0 to 1 to alpha k, alpha to the j, which was a sub kj. Okay, so that's what we're using there. Right. Okay, so now consider these two expressions. This thing here equals this thing here. Both sides are polynomial expressions in C. In fact, of degree m plus n. So this thing here, starting from here, is a polynomial in C of degree m plus n, with some coefficients, but these are unknown numbers, but still they're just numbers. And over here, this is another polynomial in C. C's are going from, well, c to the 0 all the way up to the maximum is when we get m plus n there. So it's also degree m plus n. These are two polynomials equal to each other for which values of c? For any value of c. This polynomial equals this polynomial for any value of c. Now, if you have two polynomials of degree m plus n, and they're equal, like their values are equal for any point, well, then those two polynomials are actually equal as polynomials. Right? So the two polynomials agree. Let me be specific and give you an example of what this kind of thing looks like. So, for example, if m equals 2 and n equals 1, then this equation here, this total thing, which we're calling equation 5, becomes the following. So the first thing would be a21, and then the difference here would be 1 plus c cubed minus 1. And that's the expression 3c plus 3c squared plus c cubed. That's 1 plus c cubed minus 1. And then this sum over here would be a sum, going from k equals 0 to 2 and j equals 0 to 1. So there'd be 6 terms. And you can easily check that the terms are going to be a00 plus c times a01 plus 2ca10 plus c squared a20 plus 2c squared a20 plus c cubed a21. There's a polynomial in C. There's another polynomial in C. They're equal for all values of C that you can put in. So these are equal as polynomials. That's great, because what we're interested in is determining like what the value of a sub 21 might be. And that's the coefficient essentially of the linear part of C, the term C in this polynomial. And if we look over here for things that are just of degrees 1 in C, we see we have these two terms, which conveniently have a01 and a10 in them. And we'll see shortly that that's a general situation. All right, so now let's return to the general situation. Here's our equation 5. Polynomial in C equals another polynomial in C. This one is 1 plus c to the m plus n minus 1 times a sub mn. And this one is summation k equals 0 to m, summation j equals 0 to n, m choose k, n choose j, c to the k plus j times a sub kj. Now we are going to forget about all the complexity in this formula and just focus on the coefficients of c on both sides. Okay? We're just looking at the linear terms. Forget about all the other ones. So over here, what's the linear term? Well, that's just what you get when you expand this thing by the binomial coefficient. What's the coefficient of c? It's just m plus n choose 1. In other words, m plus n. Like when you take 1 plus c to the 5th, it'll be 1 plus 5c plus other stuff. The coefficient of c is 5. Here the coefficient of c is m plus n. And there will also be this constant, a sub mn, multiplying. So that's the total coefficient of c on the left-hand side. What about on the right-hand side? In all these double sums, where are we picking up a single power of c, c to the 1? Well, there's only two ways of forming a total of 1 if you're allowed to use numbers from 0 to m and from 0 to n. You can form this 1 by taking a 0 here and a 1 here, or a 1 here and a 0 here. Okay, so the coefficients are going to be, when we choose a 0 and a 1, there's going to be an m choose 0 times an n choose 1 times a sub 0, 1. And the other way of getting it is to choose a 1 for the k and a j for 0 for the j. That'll give us m choose 1 times n choose 0 times, again, c to the 1 times a sub 1, 0 now. So this is the coefficient of c in this big expression. It's got all kinds of other higher powers of c. We're only peeling off the linear ones. Okay, there's one more rule that we haven't used yet. That's rule number A. Rule number A is the normalization one. That tells us exactly what these quantities are. A sub 0, 1 was a half, and a sub 1, 0 was minus a half. The binomial coefficients here, this m choose 0 times n choose 1, that's just n. So we have n times a half, and over here we have m times minus a half, for a total of n minus m over 2. And now we divide by m plus n, and we get what we want. A sub mn equals n minus m over 2 times m plus n. And of course, in order to do this division, we need m plus n to be non-zero. So the case m equals n equals 0 is separate, and it's easy to check that you're going to get 0 in that case. So what have we done? We've established that if there is some consistent way of assigning numbers to these signed areas of segments of polynomially parametrized curves, if there is some way which is consistent with the 5 rules that worked in the linear case, then there's only one possibility for things. The signed areas are given by the numbers n minus m over 2 times m plus n. So this is the signed area from 0 to 1 of the curve alpha to the m, comma alpha to the n. That's a fundamental formula. In our next video, we are going to look at the other half of this theorem. We're not finished understanding this, and we'll see that there's another really fundamental fact here that's might call the fundamental theorem of calculus. Okay, and that'll be interesting too. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.